Okay, so in the last lesson, I would like to give you some new introduction to how to model things in Dynamo that later you can use in Revit. So the idea is to build like a twisting tower, very simple with not that much things to do. But I would just like to explain how you can start to think on more complex geometries that you can build in Dynamo, and later you can, in such a way, import into Revit. So let me start from scratch, and I'm opening a new one now. Let me go under manual mode. So at this point, you should be able to understand most of the nodes that you have in Dynamo, but I will always try to introduce you new nodes just for you to let you know that there are nodes that probably you will never use, but sometimes you know that you can do the specific task in Dynamo. So first of all, I'm working in a project, so I'm not in a family document, and my project is completely empty. I'm going to remove also one level from here. So what we have actually in the project is just level 0. And what I'm trying to do now is to change the units from millimeters to meters, just to be a little bit more, that should be a little bit more easy with numbers. So first of all, I need to think about my my structure. I need to think about my geometry. So my geometry will be, as I said, a tower. This tower will have a variable number of floors. This tower will have a variable numbers for the distance between floors, and this tower will twist for a certain number of degrees around the z-axis. So what I need first of all is my my initial geometry, and to start I will just draw a point in the origin. So I will just create an XYZ point in the origin. Oh, where is the point? XYZ. There it is. So that's the first point. So I'm thinking to have my tower with a variable height and a variable elevation between floors. So the first thing I'm trying to create is a slider, and my first slider is the tower elevation. So if you double click on top of a node, you can easily change the name. And if you right click on top of this element, you can see that this can be set as an input for the for Dynamo. So let's see that we don't want to use 0 as a starting number. So probably the minimum height of our tower can be, let's say, 50 meters and can be up to 250 meters. And we want our step, yeah, 0.1 is okay. So the first element is this tower elevation. And for the tower elevation, between each of these meters, we want to create a new point that will be our floor level. So to do that, you know, we need to create a range, and we can create a range starting from 0, which is the first number, up to the tower elevation. So we know that now we have a tower elevation, and we want to say that we need a certain number of floors. So that's again another input that we can create. Again, we can create an integer slider this time. So we can have at least, for example, let's say 10 floors, it's the minimum. And the maximum, let's say, is probably 20 or something like that, 25. So it doesn't matter actually, it's not really important now. So this one will be number of floors. So if you take a look into this syntax, I'm using blank spaces when I'm renaming the nodes, but I'm not using blank spaces when I'm defining variables. So this is really important, because if I'm going to use a blank space here, or for example, a blank space here, I'm going to get an error from Dynamo, because we can't use variable names with blank spaces. So what I need to do now is to create this range, and I can hit run. So we have now our floors, and we have our elevation that can change, and then we can change the number of floors. So we know that if we go up with this, we have more floors, and we can adjust at least the elevation between the floors. So this can be, of course, a way to define that, or otherwise we can define this in another way. So we don't define the tower elevation, for example, but we can define the spaces between floors. So instead of number of floors, we can say that this is the floor elevation. So if we use another way to define this, we can say that the range is not using the dash mark, but we can say that the final elevation, the tower elevation, is between 0 and the number of floors multiplied by the floor elevation. That can be probably 5, for example, or again, we can use a kind of slider. So we can say that the minimum height for a floor is 3 and the maximum is 6, for example. And instead of saying number of floors, this is the floor height or elevation, let's say. So at the end, the tower elevation will be the number of floors multiplied by the floor elevation. So this is the final number, and this is 102, and this is the tower elevation and the floor elevation. So if we want to use this other way, we can fix the tower elevation in this way, and then we can change the number of floors, and finally we have a different elevation between the floors. Or we can fix, for example, the number of floors and the intermediate distance between floors, and then we can have a different height for the tower. So there are two ways to do the same thing. It depends on your design option. So I'm going to use the second one, not the first one. So let me close this one as a group so we can keep it here. This is the first type of tower. And then we can get this one, and this is the tower elevation and floors. So what I'm using, what I'm going to create now, it's a set of points using these numbers from this range. So the first one will be 0, the second one will be 6, and so on. So I'm going to connect this to the Z value, and the result will be a list of points. So as soon as I'm changing, for example, the floor elevation. So now, right now is the maximum, but I can reduce the elevation. I'm changing the elevation of the tower, or I can change the number of floors in this way. So let me put up to 10 meters here. So using these two elements, we can change the floor elevation, and we can get the center point of each floor in this tower. So the second one is to place the shape of the floor. So our tower will be kind of oval shape, so a little bit more complicated than a simple circle. And to get an oval shape, I'm going to try to do it starting from a circle. So I can get a circle, and we can say circle by center point and radius. So my center points will be these points, and my radius will be, let's say, probably 20 meters. So this can be, again, can be a kind of input. So this is gray, and this is going to be an input as well. So we have different ways to get the same result. So this is one way, actually. And the other way is to build only one circle, for example, and then try to copy this one. So I'm showing you both ways. So the other way is, let me just disconnect this one. And let me create just the first circle. So the first circle is creating at the origin. I can translate this one using a node called translate. And the translate is getting two inputs. It's getting a direction and a distance. So there are different ways to translate an element or a mesh. So be careful when you choose the translate node, that you have to find the right one, which is the geometry one, and not the mesh or the coordinate system. So I'm connecting this geometry translate to the circle. Then I'm using the direction. So we need to place a vector, and we need to find the direction of the z-axis. So we have actually the z-axis as a specific vector already available in our library. And if we type z-axis, we can get the z-axis. So we can connect right here. I'm going to show you then if you change this direction and you place the wrong direction. So the other one is the distance. We have the distance actually, because we have the distances between all the elements, so all the floors, which is the same one that we used to create these points. So we have a list here. The first one is 0, the second one is 7, and so on. So we can remove and this preview from here. We don't want to see the first one, but we want to connect the distance to this geometry. So it's just very, very, very simple. And the result is exactly the same. It's up to you how you want to achieve the same result. The next step is to squeeze a little bit these circles. Again, we have two ways to do that. We can use a scale applied to these elements. So if I'm hiding this one, this was the first step. This was the first method actually. Or we can apply the squeeze to the second one. What I'm trying to do now is to work not on all the copies of the curves, but I will continue on this with this method. So let me remove this circle here. We need the points later, so I'm taking the points with me. let me remove now this. We don't need actually yet this. And we are going to scale this geometry. Again, you have different elements where you can use the scale. We need the scale for the geometry, and we need a non-uniformly scale, because we just, oops, I hit the wrong one. Geometry scale. Okay, so we need this one actually, because we just want to squeeze around the x-axis or the y-axis. We don't need to squeeze this one around the z-axis. Let me place again a number slider. A number slider right here, so we can say that we can squeeze between 0.5 half up to 5 times, and we want to squeeze around the x-axis. So what is happening is it's not working. Why? Come on. Geometry scale. Yeah, it's correct, this one. So why it's not squeezing? Let me connect this one. And let me connect this one, and let me change this one. Yeah, perfect. So if I'm connecting now these elements, you can see that I can squeeze this around the y-axis or the x-axis, or of course, if I'm connecting this to the z-axis, nothing will happen because we cannot squeeze around the z-axis. The curve is flat. And if I'm going to connect this between x and y, I'm just getting a new circle, scaling between the two directions. I can squeeze around x and y with two different ways. So I can squeeze a little bit from here, or probably I can squeeze a little bit more from here, and so on. But the result is just something that we need here as a shape. So you can start to think how you can use these things now. So the next step is to translate, and we can translate again within a direction and a distance. So we need to translate this geometry in this direction with these distances. Pretty simple, pretty straightforward. And if we are going to change, for example, the shape here, or we can still change the floor elevation, or we can still change the number of floors, it's pretty parametric. Let me save this. Lesson 8. Okay, let's move on. Now I need the rotation of the elements. So this is a little bit more tricky because first of all, we need to create a range of elements. We need to go from 0 to up to 360 for the rotation. We are talking about degrees. This is the maximum rotation. And again, this can be something that you can decide with the slider. So this is, let me call this one X scale. And this is the Y scale. Again, those are inputs that we can get here. And this is the shape radius. So let me connect these two and add to group. Okay. And this is connected to this. And again, I want another slider, another integer or number slider that can go from 0 to let's say from 10 degrees to up to 360 degrees. And this is the tower rotation. Again, we can add this to the group and we can connect this to the maximum rotation. And now we have the number of rotation. What we need is exactly how many rotations we need between the first number 0 and the maximum number, and this is going to be actually the exact amount of floors that we have. So we need exactly 20 or 24 rotations because we have 24 floors. So you can count this list or you can just connect number of floors. Again, you can connect directly this. And this is going to be an dash. And we have now all our rotations between 0 and 10. But be careful because we have exactly 25 points because we need to count also the 0, 1. And we have 25 curves here. So we need the number of floors plus 1 because we need to count also the 0 level. And now we have from 0 to 10 with 25 elements. Be careful when you count the elements because you have you need the same exact number of elements. And again, we can move and change the number, the maximum tower rotation, and so on. Let me hide this curve, which is the first curve. Let me hide this, that is the translated curve. And let's create now the rotate geometry. The rotate geometry is taking a geometry, of course. So the first one was the circle. The second one was the scaled version of the circle. The third one was actually the translated versions of the scaled circle. And the last one is the rotation of the translated version of the scaled center radius circle. The origin of the rotation will be exactly the point. So that's why I kept the point from the beginning, because we need the point now as a center point for the rotation. The axis of the rotation is still the Z axis right here. So we can reuse this. And finally, the rotation value in degrees is what we have calculated right here. And that's the final one. So now we have our tower twisting actually, and we can change the rotation of the tower. I'm keeping here the tower just to see the tower a little bit better. And we can change still the scale. We can change the Y scale, and we can change the maximum rotation in these directions. And we can still change the floor elevations, or we can change the number of floors. So it's pretty nice that we can still change everything. If you keep variables along the way connected to integer sliders or connected to elements that you can change, you can still use your parameters up to the end of the project. Now let me align this from here, and I want to remove this from the group because they are not part of the group actually. I need just this one. And 20 is the shape radius. Also this one can be a slider. And number slider from let's say 10 to 50. And let me connect. This is the radius. And I can connect now this up to the radius here. So I can get rid of this and I can add this to the group. Voila. Pretty nice. So let me save and we can continue. Pretty simple. You will use a lot this geometry scale or geometry translate or geometry rotate using points as a origin, or using, for example, axis for the rotation. It's really easy to use this one. Now those actually are the shapes for my floors. What I need to do before going to Revit actually is to build a shape for the shell of the tower. And to do that, I'm going to offset. So curve offset. I'm going to offset these curves with a specific distance. Again, the internal one and the external one, the basic value is 1, but again, I'm going to create here a new slider, and this slider is again a number slider. It can be from 0.5 up to 2 meters, and this is the shell distance, except again, I can add this to this and add to group, and connect now this one to this one, and save and change the shell. I can make it bigger or smaller, and up to here we just have the initial shape. Now we can start to build on top of this shape. So first of all, I'm going to create the shell. So the shell is actually a surface by cross sections. I'm gonna cross section with using these curves. Actually, the latest one, because I want the cell a little bit bigger than the other. Sometimes what you can get is that you have a problem with surfaces because it's not a NURB curve. So when you have these curves, first you need to be careful and you need to convert these curves into NURBS curves. And you will do this a lot of times actually. How you can do that? To be able to convert a curve into a polycurve or a NURBS curve, you need first of all to create a discretization of the curve. And to discretize, to evaluate, how is called this operation, the curve, you need to create a couple of points around the curve and then interpolate with these new points. How we can do that? We have a specific, we already used actually this point at parameter. And as I explained many times, the parameter is just the length of the curve from 0 to 1. So it's just an x value related to the curve, is a u value actually it's called, and it's going always from 0 to 1. It doesn't matter the length of the curve. If we need to rebuild this curve based on new points, first I'm going to remove the preview of this and the internal one. And then I need to create a new range of numbers from 0 to 1. This is not going to be a variable because it's always from 0 to 1. What is can vary is the number of points I want to use to discretize this. And this is again going to be this time an integer slider that can go from, let's say, a minimum of 10 points up to 100 points. And I can connect this now up to here. And this is the new list. Remember, whenever you have a list of different length, because this one is 27, those are 27 curves, and those are actually, sorry, the dash, and those are actually 10 points. What you need to do to be able to connect both of them is to use a different lacing, because otherwise what you will get is a point on each curve up to 10, but you don't need this. What you need is actually this. You need 10 points on each one of the curve. And after you do this, you can create NURBS by points. And that's what you need. So as much as you add points to this curve will be closer to the initial one. It's just like a discretization of the curve. And now, let's say we want probably 20 points. And now what we can do is to build the surface. Surface by loft cross sections. Those are my curves, and this is the cross section. So finally, we have our surface. Remember, this part is basically always needed. When you need to go from a simple, let's say, mathematical curve like this curve to something that is buildable. So it's you have to go always through this rebuild of the curve. Let me group this one, and this is rebuild the shell curves. Now that we have the shell curves, we can start to rebuild also the internal one. And I can copy and paste this. I can go here and I can connect this curve instead of the other one. I can hide now the shell. I don't need actually the surface. I just need only the curves. Oops, I used one. I can hide the points and I can get just the curves. So right now it seems that they are exactly the same like the first one, but they are new curves. They are actually now NURBS curve. Let me try, this one are the floor curves. And I can save. Now it's time to think about Revit. First of all, we need, Okay. First of all, we need to create levels. We don't have actually levels. And we have specific nodes in Dynamo to create new levels. And those nodes are level by elevation, for example. I need just elevation here. We have elevations because we have the initial shape elevations. Just we already have the level at the 0 elevation, so we can remove this from the levels. And to do that, we have a specific node to remove the first item from a list, and it's called rest of items. Rest of items is always used when you have list with the header, for example, or you want to remove just one element from the beginning of a list. And that's exactly what we need now. I'm going to switch to manual mode. So now we have only the remaining elements to create levels. And if I run now, I have my new levels. They are not visible, of course, in the floor plans because we just created levels, not floor plans. But as you can imagine, if I change this into automatic and I change floor elevation, for example, and I change number of floors, you can see that we have new floors every time. Of course, the shape of the element is changing. And what we need now is actually build floor plans for this. Again, we have floor plans by level or ceiling plan by level. And we can connect to both of them the same levels. Run. And in just 2 clicks, probably, we have bunches of ceiling plans and floor plans. I'm not going now to rename these levels. It's not really important now. You know how to do that because you can use the set parameters name by name, sorry. So I'm not going to focus on this one. You do that. And this is Control G, and this is create levels and plans. What I want to create now is are actually the floors. So how to create floors? Again, we have a specific node to do that. We have floor by outline. Be careful, you have 2 different. One is outline curves. If you have multiple curves creating the shape, the outline shape. In this case, we have only 1 curve, so we need to use the second one. We only have the outline curve. Starting from this, of course, because those are the shapes of the floor, we can connect the outline here. And we need the floor type, where we can select the floor type. Oops. Yeah, sorry. Floor types. It's this one. And from this, we can say, I want to use the generic, this one. Remember, this is always going to be an input. And this is going to be the integer value. It's the number of points. So number of points for curves. And this is add to group, and this is floor types. Voila. So we can connect this to this. And levels, we already have levels, and we can connect levels from here to here. Let's see what we can do now. I can click run. but I'm still getting an error. Why? You have to always check the input type of the elements. So this kind of surface is getting curves and NURBS curves in this case. But this kind of element is getting as an outline a polycurve, not a NURBS curve. They are different. The NURBS curve is a curve with a degree 3, so it's a cubic curve. The polycurve is a curve with a degree 1. It's actually a linear curve. We can create a polycurve by points in the same way. We just need a different node. This is going to be polycurve by points and not NURBS curve by points. So I can remove this one and I can use polycurve. So finally, let me go in 3D and I can click run now. Boom. It's actually a floor following the shape of the element. And these kind of lines are because I'm using only 20 points to create this. So I can parameterize again this one, saying that this is the number of points for NURBS and this is the number of points for floors. And this can be probably even up to 50, it doesn't matter actually. So I can create this with a different number of points. So as much as you go up with the numbers, you will get a closer shape to what you need. And this is actually the real construction situation. You can get an oval shape. You just need to interpolate these edges, even if you are going to construct that. If you want a little bit more closer to the end, you can squeeze more this one. You can say 80. It doesn't really matter actually. But as more points you insert here, you can get a closer shape to what you need, and that's probably what I like. So that's pretty easy, and I can switch between the levels. I have my levels, and that's something really nice. The last but not least, I'm going to build the shell now. So bear with me a little bit more. I need to do an intermediate step because I want to create panels. And to create panels, I need to split my surface. I can just use again my shape now. I need to hide this probably. I don't need it. I can hide also this polycurves. So just I need to see the shell. There is another very common common package called Lunchbox. Oh, come on. This package is probably the most downloaded package in the Dynamo package. Everybody's using this. It's really common. And again, you can search for Lunchbox in the package repository. I have already downloaded and it's right here in my library. What we need is called Quad Panel. And to create a quad panel subdivision for a surface, we need a surface, of course, and we need the number of subdivision along the X direction and the Y direction. what we can do for the X direction is to split by the number of points. So 20 points actually. And we can connect this using this 20 as a value. And for the V value, we can use the number of floors. So that's probably the best way. Let's say 27 and yeah, that's it. And we can connect this one. So that's the real power of nodes. You can always reconnect the output of something into the input of something else. And you can get the data, the flow of the data always connected. I'm gonna run. It's a pretty nice surface. It will take probably a couple of seconds to do that. Come on. Okay, so finally we have these points and we can hide actually the surface. And this is the, let's say, panelization of the of our surface. And that's pretty amazing if you can see it. It's really powerful. But how we can use now all of these points to be able to create something in Revit? So the only way to do that is to create adaptive points elements. I don't know how much are you familiar with the adaptive points. I really suggest you to go and have a look if you don't know how to use that. But you can create a new panel based on adaptive points using a new family, Revit family template, and you can go to searching for generic model, and the one you need to use is the pattern based, just to create panels. So let's say, okay, you have these 4 elements right here, and you can create, for example, a basic, really basic shape, just to create a simple panel. Very simple. So the good thing is that this will always adapt to the position of the panels. You can create really complex shapes. I'm not going to focus now on this. I'm just saving this as a family and saying this is lesson 08 panel. And I can load this one. So how the panel is working actually is very simple. You have these elements, and no matter where you click 4 points, you get always a panel. So that's pretty nice, pretty amazing. And we are going now to put this panel on top of our element. If you don't want to follow a square panel, you can also create another one. You can create a family, this time using the generic model adaptive, so not the pattern based. And you can just go up to the floor level. You can create 4 points. You can select those points and make them adaptive. So this is 1, 2, 3, and 4. And then you can connect these elements and using this way. And then you can actually create again a form this way. And again, you have your elements. So pretty nice. I can give also a material here, and this can be renamed as a glass. And use render appearance, create a new material. Oh, we already have glass. Okay, that's pretty fine. Okay, we need transparency as well. Okay, I think I had a problem with the connection, but don't worry, I'm back again. And so I just created an element here. Again, this is another panel. I just placed colors here. So this is a little bit more advanced compared to the previous one. And this is going to be probably 10 centimeters or 5 centimeters. So we have a glazed panel that we can use in our project again. So what we can do now with this is to go inside Dynamo and use those points. We have lists of points here, and we can create adaptive components by points. So we can connect points and we can connect a family type. The family type is actually the panel family. And as always, this panel family is going to be an input. Add to group and family types and lesson 8 panel adaptive and connect to this. And I just would like to group these two and give a bluish color, create floors, and create panels. Let me save and run. I have really bad connection here, and I'm going to share again the screen just to show you the connection here. It's already finalized. So this is the glazed panel on top of the tower based on our shape, and it's perfectly following our shape. You can improve actually the element, just creating, for example, but that's obviously it's more Revit. Let me set, for example, this one. Pick this one. Let me show this and this, and I can create probably a small form here. Why not? I can create a point here and set this and create a shape, and I should be able to create a form. Well, so I can load this one back to the project, and that's it. Of course, now I have intersection, but I can create a better way to see this panel, and I can create more complex panels here. I can calculate the deflection of the panel. It's really something that you can create. You can manage also these parameters from Revit or from Dynamo. It's really something that can be quite amazing if you start to use in a proper way both Dynamo and adaptive components. I'm using quite everyday adaptive components in my day-by-day activities. So it's probably one of the most powerful tool that you can use in Revit. Oh, let me go and change the glass. Override this. You can definitely control almost everything from here, and you can probably create stunning visualization from here, creating cameras and creating sections and blah blah blah. So that's something that definitely you can't create manually in Revit using simple elements, because that will be really complicated. And if you are preparing a tender, or you are preparing something that you have to show to the client quickly, and you want to create complex shapes like this, you can definitely do it with Dynamo and Revit together in probably a couple of hours. It depends on the complexity of the shape, but it's pretty simple to do that. So let me save now this one, and I hope you enjoyed the last lesson. I'm going to send you this this file together with the panels and whatever it is. And please, if you need any help after the course, I'm going to help you with. If you send me an email and you have any kind of trouble, I can suggest you probably the solution, or I can help you to find the right solution. So if you start to do some exercise, please let me know, and please share with me. Let me save this, and that's it. So thank you for everybody for the time we spent together, and see you soon.